Okay.
Yeah, so I will talk on attention and its various forms. So flow of the presentation will be, uh, first of all, I will give some background on attention, like what is attention and why it is needed. Then some formulations of attention. Then how the alignment scoring is done, that is how attention scores are calculated. Then what are the various functions that are explored for calculating attention scores. And then finally, I will end up with one more attention formulation, that is self-attention. So what is attention? So if we take the example of machine translation, um, um, for generating some target word, we need to focus on only some of the words in the source sentence. But in sequence to sequence architecture, we used to depend on only one fixed length vector, with where all the sentence information is captured in that vector, and that is given as input to the decoder, and decoder, all the stages of decoder tries to generate the target word only on the basis of that particular vector. So problem with with the attention, for any decoder stage for generating that particular target word, we compute the score for each encoder stage, which will denote how important that stage output is to generate that particular decoder stage output. So it basically frees the model from having to encode whole source sentence into fixed length vector, um, and let the model focus only on the relevant information. Uh, regarding architecture, I will talk on that in the later slide. So why attention is needed? So in the Bahadanuj attention paper, so they have given this example of longer sentence. So they were translating from English to French. When this was given to the sequence to sequence encoder decoder architecture, it was correctly translated until a medical center, like till here, but then it deviated from the original meaning of the sentence, and wrongly translated based on his status as healthcare worker at a hospital to based on his state of health. So this might be because loss of information like word order information in the fixed length encoded vector taken from last encoder stage. So attention in such scenarios of longer sentences will help us, to get the target translation as based on his state of health. Using attention, we will focus on only these set of words. Um, so here I will talk about some attention formulations. So one of them is global attention model. So in global, for uh, attention scores are calculated for all of the encoder stages, uh, for determining, like in this figure, for all of these are the encoder stages and these are the decoder stages. So in the global attention model, we consider all the encoder stages and determine importance of each one of them as a attention score. Whereas in local attention model, what we do is we only consider a subset of encoder stages to determine the importance. Now, how we compute that which stages, for which stages we should compute the attention score. So in the launch etc. all 2015 paper, they have used two strategies for that. One is monotonic alignment, So what is monotonic alignment is they have assumed that for the ith source sentence word um, will be translated to ith target sentence word. So alignment is monotonic. So and having this assumption for ith word in the source sentence, they consider I minus d and I plus d as a context of that particular word, and only consider those encoder stages. Only calculate attention scores for those encoder stages, and yeah, and in the and second strategy was predictive alignment, where they predict the context on the basis of um, so this was the formulation for predicting the context. So S is the length of the whole sentence, and sigmoid of VP transpose is the VP, and V and W are the trainable parameters, and ST is the uh, target hidden state, that is target decoder hidden state. So S is the length of the sentence. Sigmoid will give us some value in between 0 to 1. So if it is 0, then context length will be 0. If it is 1, then context length will be the whole sentence. Then in one of the image caption generation paper, they have used two types of attention, that is soft attention and hard attention. So soft attention is similar to global attention, where we context vector is weighted sum of all encoder hidden states. And in the hard attention, we calculate attention score for all encoder hidden stage, and only the stage for which the attention score was max will be used for target word generation. So that was hard attention. Uh, so how we compute the alignment score, basically attention score, is suppose this is the encoder layer and this is a decoder layer. Uh, so as and these are the encoder hidden states, that is encoder output for the input, and then for the first decoder stage we provide the last encoder stage output as its hidden state input, and then so after getting the first decoder phase output, suppose this is the first decoder hidden state. Now the our problem is to compute for this particular decoder stage out of all the encoder stages, which are the most important stages. So what we do is on the basis of previous decoder hidden current decoder hidden state, and for each encoder hidden state we will compute here in this example I will take dot product. So in the decoder I will take dot product of encoder hidden state with the decoder hidden state. Score will be computed, and then in the similar manner score will be computed for each encoder stage, and then we will take the softmax, like so as to have the score sum to 1, and then now this is the weight of each encoder hidden state that denotes its importance. We will multiply that with the encoder hidden state, so that by that factor the importance of that like weights of that particular hidden state will be increased. In this way we will obtain hidden state values for each encoder, and then to form a context vector just with the addition of all these weighted encoder hidden state outputs, and that will be given as an input to the decoder stage. Along with that, the decoder stage input will be previous stage output. So yeah, so this is how the alignment score are computed. So here here just a small example. Suppose decoder hidden state is 10 5 10, and encoder hidden states are like this. So score for first one will be 10 into 0 plus 1 into 5 plus 10 into 1. So it will be 15. Accordingly, encoder other encoder hidden state will be weighted, and then from here we can see the second one is the most important for second decoder stage output generation. Uh, then there are different ways to compute these alignment scores. So in the Mahadenu, that is origin paper of attention, they have used this additive concat way. So what they do is they just concat decoder hidden state output and encoder stage output, and then uh, then here that is the equation we have. So we just multiply with them with the trainable parameter, and then we apply 10h activation function on this layer, and again they will be multiplied with some trainable weights, um, and we generate the score. So so that's how we generate the score. So in the attention layer as well, we have trainable parameters in additive concat method. In the dot product, we just take the dot product between decoder hidden state and encoder encoder stage output. So it will essentially determine the similarity between them, and will compute the score. In the scale dot product, it is just we just multiply the dot product. We just scale the dot product by inverse of uh, dimension of source hidden state. So mm, in the encoder stage output, if there are n number of units, then we scale it by that. In the cosine similarity, computes cosine similarity between decoder hidden state output and encoder output, and compute that will give us the score. And in the general method, it's like so if the equation is over here. So first of all, we encoder, this is HS is the encoder hidden state, that is source hidden state. We multiply it with some trainable matrix, that is W, and then the output of that we will multiply with target hidden state, that is decoder hidden state, and then we will get the score. So these all the different scoring functions are experimented by Long in 2015 paper, and according to him, the dot product perform best in case of global attention, whereas general scoring function performs best in case of local attention. So coming to the last formulation is the self attention. This one is used in transformer architecture. So here what they do is first of all for so we compute attention uh, only on the basis of input. So we do not utilize the decoder stages. So what we do over here is each input will have three trainable uh, three vectors, that is query, key, and value. Um, and then initially the values of these will be obtained. So there will be some trainable matrix. On the basis of that, uh, so suppose we have some trainable matrix T, we will multiply that with the input, and we will get query, key, and value for each one of the input. Now after getting query, key, and value for each one of the input, uh, we just uh, now the problem is to determine attention score for say first input. So what we will do is the query vector of that input will be multiplied by key vector of each one of the input. So and we'll just take the dot product. So here we can again use any scoring function here. Let's say we are using the dot product. So query so here we'll so that's how we'll get these scores, and then we will apply the softmax on the scores so that the scores will range with their sum will be 1, and then we multiply the value vector with those score, the respective scores, and that's how we will get these uh, weighted what we can say is value matrix, and then the context vector just will be the addition of all of these, and this will show the importance of for the first decoder stage. So this will show the for the first decoder stage the importance of first input is 2.0, the importance of second is 7.0, and importance of third input is 1.5. So that's how the attention weights are calculated in self attention. In the next talk, I will cover multi-head attention and how attentions are used in CNN architectures.